Hello students. So today in this lecture we are going to discuss for the revision of the syllabus from electric potential to capacitance for your examination purpose. Okay. So first of all we are going to discuss what is electric potential and potential energy. Electric potential energy. So what is electric potential energy? We already studied about the potential energy in your 11th syllabus during the gravitation chapter. So potential energy is defined for the work done in a conservative force field. That means the field in which the force is conservative. So conservative force means the force which is independent of the path followed. So when we do some work in a conservative force field, that work is stored in the system as potential energy. So what is electric potential energy? That means when in an electric field we have to bring any charge from infinite to any place within that field, then that amount of work done by the external agent to brought that charge from infinite to that given position is stored within the system as electrical potential energy. That means if here is a source charge Q and I am routing a positive test charge Q naught from infinite to any position within the field region of this source charge which is at a distance r, then the work done by moving this charge from infinite to this place will be stored within this system as the potential energy. So what will be the potential energy at this point P? For this source charge Q will be how much? K Q naught by the distance from the source charge to the position where we want to calculate the potential energy for this system will be R. So this is the expression for electrical potential energy at this place. And this electrical potential energy is what? The amount of work done by bringing this charge from infinite to this place by any external agent. And you have to remember that in this formula, the potential energy where K equal to Q naught by R, the both charge Q and Q naught are must used with their sign. That means if here the Q is negative, then we have to replace this. The potential energy at point P will be K minus Q naught by R. If Q naught is negative, then also the potential energy at point P will be K Q naught negative by R. If both are negative, the potential energy will be how much? K minus Q naught by R, which can be K Q naught by R. So you have to remember that during the calculation of electrical potential energy, both the charges are taken with their signs or polarity. So when both the charge are negative, the potential energy of the system is positive. When both the charge taken are positive, the potential energy of the system is positive, but only when the two charges which are taken within the system have opposite sign. That means one is positive if Q naught is negative and Q is positive, then only the potential energy of the system will be negative. Otherwise, the potential energy of the system will be positive. So you have to remember in the formula the potential energy of a two charge system, which can be given as K Q1 Q2 by R, where R is the separation between two charges and Q1 Q2 are the two charges of the system. Then the potential energy of this two charge system will be this much, where the Q1 and Q2 are represented with their symbol. That's why the potential energy will be negative only when these two charges have opposite polarities, and it is positive when the charges have same polarities. Clear? So this is about the electrical potential energy for two charge system. And what is the unit of electrical potential energy? As we already discussed, that this is the amount of work done by bringing a charge from infinite to any place. So these have the unit same as that of work done, that is joule in SI or org in CGS, and dimension same as that of work done, which is equal to M1 L2 T minus 2. Clear? So this is about the electrical potential energy for two charge particle system when there are more than two charge particles. Suppose I have three charges Q1, Q2 and Q3, and I want to make a system which have these three charges. Then what is the total potential energy of this system? So the potential energy is the amount of work done by arranging or making this system. So the total potential energy will be the work done by bringing first Q1 charge from infinity to one place. If this is the place of Q1, so I have to place this Q1 from infinite to this place. So initially there is no electric field, so I have to do zero work. So first initially I place Q1, so zero work will be done. Then the work done of Q2 by replacing from infinite to certain place, let here the distance is R12. So the work done by replacing Q2 from infinite to this place, what will the work done within the electric field of Q1 will be the potential energy for these two system of charge, that can be written as U12 will be K Q1 Q2 divided by R12. Similarly, when I have to place the Q3 at this place, such that the distance from Q2 will be R23 and from 1 will be, it will be R13. So now when I am placing Q3 from infinite to this position, I have to do work against the field of Q2 and as well as against the field of Q1. So the total work done by placing this Q3 will be stored within as the potential energy for this system. So this can be written as the potential energy on Q3 due to 1 will be K Q1 Q3 by R13, and same as that of 2 3 will be K Q2 Q3 divided by R23, and this is the total potential energy for the making of this system. So the net potential energy for the 3 charge particle system will be how much? Okay, similarly you can calculate for further more large number of system of charges, but the probability question asking in the examination maximum up to 3 system of charges. If there are more, then you can do like this. And the total number of pairs, how you can calculate the total number of pairs for n number of charges will be how much? N into n minus 1 by 2. So this is the total number of pairs when there are n number of charges or a system having n number of charges, and we have to calculate the net potential energy. For that we have to first calculate there are how many number of pairs, like this 1 2 2 3 1 3. So there are this number of pairs for n number of charges, then we have to calculate the potential energy for each pair, and then we can add them to get the net potential energy of the system. Okay. And similarly for calculation of each pair we have to take the charge with their signs. Here all the charges are positive, that so that I can take all the charges are positive. If there are some of are negative and some of are positive, then we have to take the charge according to their sign. Clear? So next, what is electric potential? So electric potential energy is the amount of work done by the external agent to bringing any charge from infinite to the given position within the electric field of the source charge. So in case of electric potential, if this is a source charge at this place and I have to find out the potential, electric potential at this point P. So the work done by bringing a unit positive test charge when Q not equal to 1 from infinite to this place P, then that amount of work done by the external agent will be the electric potential at this place. Clear? So we know the potential energy for bringing Q naught will be how much at point P? K Q naught by R. If this distance is R, then the electric potential at point P will be, when Q naught will be taken as unit, so this will be how much? K Q by R, or this can be written as UP by Q naught. That means the potential, electrical potential at any point or any region within the electric field of a source charge will be the electrical potential for unit positive charge, unit positive test charge. Clear? So V can be written as by Q naught, or from in, this is the potential at this place which is independent of the test charge. That means the electric potential is the property of the location. So at this distance R from the point Q, if I place any charge, the potential will be same. This is the property of this location. So at any place which is at a distance R from the source charge, the potential will be remain constant. If I change the distance, let this is the position P dash. So at this distance where the source charge is at a distance R dash, So at all the position which are the distance r dash, the potential will remain same. Maybe the test charge varies, but the potential at this point will remain constant. So the electric potential is the property of the location, but electric potential energy is the property of the system of charges. So when we change the charges, the potential energy will change. But if we change the test charge, the potential remains same until the source charge remain constant. Clear? So what is the unit of electric potential? As this is potential energy per charge, or same the potential energy as work done. So work done by charge, it will be how much? 1 joule by 1 coulomb is the unit of potential, or this can be written as 1 volt is the potential in SI system, and in CGS system we can have 1 start volt. Okay, so there is an important relation between 1 start volt and 1 volt. You can remember this for your examination purpose, that 1 volt will be equal to 1 by 300 start volt. You have to remember this relation. And what is the dimensional formula for electric potential? As potential V is equal to potential energy by charge, or this can be written as work done by charge. So this can be the dimensional formula will be work done dimension M1 L2 T minus 2 divided by the dimensional formula for charge is AT. So from this we can get the dimensional formula M1 L2 T minus 3 A minus 1. So this will be the dimensional formula for electrical potential. Okay. So what is the electrical potential due to a point charge? As we already discussed that if here is a point source charge Q and we have to find out the potential at this point P, which is at a distance R. So the electrical potential at this place will be how much? V equal to K Q by R. This is the expression for what? The potential at this point P due to this point charge. And here the charge Q is take with respect to the symbol. If Q is positive, the potential is positive. If Q is negative, the potential is negative. That means if your Q is positive, this is the potential at this point P. If we take Q equal to negative, so the potential V at P will be how much? K minus Q by R. Clear? So in case of potential, the charge is also taken with the symbol or polarity. If it is positive, the potential will be positive. If it is negative, the potential will be negative. So what is the work done at this place? As we know, the work done W equal to Q into V. So in this formula, the Q is also taken with respect to the symbol. This is the work done by the external agent. So work done by the conservative force or the electrostatic force will be how much? Minus Q into V. Because negative work done of conservative force will be stored as the potential energy. So this is same as the potential energy, and this is also equal to the potential energy. So the negative work done by the conservative force equal to minus QV, which is equal to potential energy, or the work done by the external agent equal to QV. This is minus term. Okay, so from this we can write the work done is also Q into V, where Q is taken with respect to the sign or polarity. Okay, so when there are, we already know for a point charge the potential is given as K Q by R, where R is the distance of the position or location where we have to find out the potential due to the source charge Q, and here Q is taken with the sign of the charge. If it is negative, the potential will be negative. If it is positive, the potential will be positive. If there are a large number of charge, here is a charge Q1, Q2, Q3 and Q4, and we have to find out, this is the position A, B, C and D, and we have to find out the net potential at this point P, where a charge, let be the charge will be unit. We have to find out the net potential due to all these charges at A, B, C and D. The P, the distance from Q1 will be R1, this will be R2, this distance is R3 and this distance is R4. Then what will be the net potential due to all these charges at this point? So we can write the V net at P will be how much? Potential due to Q1 plus potential due to Q2, that of 3, that of 4. So this can be written as K Q1 by R1 plus K Q2 by R2 plus K Q3 by R3 plus K Q4 by R4. So this will be the V net at the position P due to all the charges surrounding it, and all these potential are again also taken with respect to the sign of the charges. If Q1 is negative, so here we have to put minus K Q1 by R1. If Q3 is negative, we have to put minus K Q3 by R3, and accordingly we have to add them. Clear? So potential at a point due to a system charge is this much, potential at a point due to a single point charge is this one, and the potential, electric potential, is depends upon the sign of the charge. For positive charge it is positive, for negative charge it is negative. Clear? And put the unit of potential is volt or joule per coulomb in SI and start volt in CGS, and the relation between volt and start volt is 1 volt equal to 1 by 300 start volt. Okay, and potential is a scalar quantity because it is independent of the direction. Then what will be the variation of potential with respect to the distance? So if here is a source charge Q and here is a point P at a distance R, so what is potential? V at P is equal to K Q by R. So from this relation, K is constant. What is K? K equal to 1 by 4 pi epsilon naught, we already know, and Q is the source charge which is remain constant. So from this relation we get what? The potential at any point P is inversely proportional to the distance from the source charge. So if we plot the graph, this is the potential and this is R. So Vp is inversely proportional to R, so the graph will be like this. And this is the expression when charge is positive, that means when Q is greater than 0. So this will be the relation when Q is greater than 0. And if I take Vp with respect to 1 by R, so Vp is directly proportional to 1 by R, so the graph will be like this. Okay, Vp is directly proportional to 1 by R, and this is the relation when Q is greater than 0. Okay, but if in this formula the charge is less than 0, that means negative. So if Q is less than 0, so what is the graph between Vp and R? Vp will be negative, so the graph will be in the fourth quadrant like this, minus Vp. Okay, and what is the graph between 1 by R? Again Vp is negative, so the graph between 1 by R will be like this. Okay, clear? So this is the graph for potential with respect to 1 by R when Q is less than 0, and here also Q is less than 0 or negative, and this is the graph when charge is greater than 0 or positive. So you have to remember that during the calculation of electrical potential energy, we have to take the charges with their symbol or sign, and also during the calculation of potential we have to take the charge with their signs. Okay, so next we have to study. So this is all about electrical potential energy and electric potential, how to find out the potential due to a system of charge, how to find out the potential energy due to a system charge, when the potential is negative, when the potential energy is negative or positive, we already discussed right now. So next we have to study what is the relation between, or what is the potential difference So potential difference means if here is a charge Q at a certain place and we have to find out the difference in potential. We already studied that the electric potential is the property of the location. That means if we are moving from one point to another point within the field of the source charge, then what will be the potential difference? That means this is a source charge and it's spread over the field surrounding it, and there is 2 points A and B. Okay, which are at the distance RA and RB. So what is the potential difference when someone moves from point B to point A? we already studied that the potential difference from point B to A when someone moves from point B to A. So the potential difference from B to A when someone moves from B to A will be the final potential. That means the potential at A minus the potential at B, initial potential. Clear? So this is known as the potential difference between B and A. So you have to remember that when you have to calculate the potential difference between two locations within the electric field of certain point charge, then you have to find out the potential at the final position. That means the charge or from where you have to move to the point where you have to move. So the final potential at the final position, which will be subtracted by the potential at the initial position. So when I am moving from point B to A is the final position and B is the starting or initial position. So the potential difference between B and A will be the potential at final position A minus potential at initial position B. So this can be written as how much? The potential at B will be how much? K Q by R A minus K Q by R B. So this can be written as K Q into 1 by R A minus 1 by R B. So this will be the potential difference when someone moves from B to A. Clear? So this is known as the potential difference. This is also have dimension unit same as that of potential, because this is a potential difference means also it's equal to potential. So you have to remember, when you have to calculate the potential difference between any two points, you have to find out the potential at the final position, then the potential at the initial position, and take their difference. So the potential difference between any two positions will be the potential at the final position subtracted by the potential at the initial position. Okay. Next, we have to calculate the potential due to a dipole. We already know what is a dipole. When two equal and opposite charges are separated by a very small distance, they form a dipole. So let this is a dipole having minus q and plus q charge, and length of the dipole is 2l. So if you have to find out an axial position P which is at a distance r from its center, then what will be the net potential at this point due to the dipole? We already know the potential at this point due to the positive plus charge. We can already calculate by which will be equal to the distance. Then we have to find out the potential at negative, because during the calculation of potential we have to take the charge with their sign. Then the net potential at this point P will be how much? We already discussed about it detail in the previous lecture. So it will be Kp by r square. For ideal dipole case, when the distance r is very greater than in comparison to the length. For ideal dipole, that means r is very large than L, length of the dipole. The potential at this point will be Kp by r square. Clear? What is P? P is the dipole moment. So P equal to how much? 2L into Q. So this is the potential at this point P due to the total dipole or any axial point. So same as that of any point on the equatorial line which is at a distance r. So as the distance of the charge on the equatorial line is at a distance r from the center, so its distance from the negative charge and positive charge will be same. So the potential at this point is same due to the negative and same as that of the positive. So the net potential at this point will be 0. So V at equatorial, you have to remember, point is 0 due to a dipole, because the potential at take with respect to the signs of the charge. So at equatorial point due to a dipole, the net potential is 0. You have to remember this. And at an axial point, the potential is this much. But if there is any arbitrary point, so if this is a dipole having minus q charge and plus q charge, and this is the length 2l, and from center there is a point P which is at a distance r and makes an angle theta with the direction of dipole moment, which direction is from negative to positive, then what will be the net potential at this point? This is an arbitrary point. So the potential at this point P will be how much? Kp by r square into cos theta. This is the expression for potential due to a dipole at any arbitrary point, where P is the dipole moment of the dipole, r is the distance of the point of observation from the center of the dipole, and theta is the angle between this position vector of the observation point with respect to center of the dipole and the direction of dipole movement of the dipole. So this is the expression for electric potential due to a dipole at any arbitrary position. So from this we can easily calculate the potential for equatorial and axial, because at axial theta is 0, so this will be Kp by r square, and for equatorial theta will be 90, so this term will become 0. So this is how to find out the electrical potential due to a dipole at an axial point, equatorial point, at any arbitrary point. Clear? And the derivation, for the derivation you can refer to the video that's sent to you earlier. Next is what will be the relation between electric field intensity and electric potential. So from previously we already discussed that the electric field intensity E equal to how much? Magnitude of electric field intensity. Here electric field is a vector quantity, so its magnitude will be k q by r square. If here is a charge q and at a distance r there is a point of observation p, so the electric field intensity at this position will be this much. Same as that of V at that point, E at P. V at P will be how much? K Q by R. So from this we can derive the expression that the potential V is equal to how much? Or E is equal to, or you can write V, the potential is electric field E is equal to minus dV by dr. This is a vector symbol. So from this, magnitude of this can be taken as this much, or in vector clearly you can write the E vector will be equal to minus del by del x into V of x I cap minus del by del y into V of y j cap minus del by del z into V of z k cap. Okay, this is the relation between electric field and potential, or simply we can write E vector equal to minus del by del r V. Clear? Where del by del r is the del operator, or simply this can be written as E vector equal to minus grad dot V. Okay. Clear? This is the relation between electric field and potential. For the derivation you can refer to the video, or if I take the inverse of this, so the change in potential will be equal to minus integral, line integral of electric field, or this can be written as V initial minus V final will be equal to the line integral of E vector dot r vector, the line integral of electric field. So this is the relation between electric potential with respect to the electric field. If the question is asking that prove that the potential difference is the negative line integral of electric field, then you have to determine this relation, derive this relation. If the question is asked that the electric field is the negative gradient of the potential, you have to derive this relation. But these two are interrelated to each other. Clear? So from this we can write, if the electric field and dr can be written as dr vector mod E vector mod integration of cos theta. Clear? This will be what? V initial minus V final. Okay. And this relation we can write E equal to minus dV by dr. That means if the graph between V and R is given, the electric field will be negative of the slope of the V versus R graph, because this is dV by dr. So if the V and R, the graph will be this one, so the negative of the slope, this is the slope of dV by R, so electric field will be negative of this slope, so this will be what? The E for the graph between V and R. Clear? So in V and R graph, the slope, negative of the slope will gives us the electric field, and in this case the area between E and R gives us the negative of the area between E and R gives us the potential difference. Clear? So you have to remember that in electric field versus position or distance graph, the area gives us the potential difference, negative of the area gives us the potential difference, and in potential and position graph, the slope, negative of the slope gives us the electric field intensity, and the relation will be electric field intensity is equal to minus del V by del R, and the potential difference will be minus negative of line integral of electric field intensity. Clear? So next we have to discuss that what is equipotential surface. So equipotential surface, as the definition says, it is a surface where each and every point have same potential. So if I am considering here is a surface and all the points lies on this surface have equal potential, then this surface is known as an equipotential surface. That means when each, here is a point, here is a point, or any point on this surface have equal potential, then this region or surface is known as equipotential surface. What are the properties of this equipotential surface? So properties of equipotential surface, as the potential at each and every point is same, so the potential difference between any two points will be 0. So the work done by moving a charge from one point to another point on the equipotential surface is 0. Again, the electric field lines are always perpendicular to the equipotential surface, as there is no work is done. So the angle between electric field lines and the surface of the equipotential surface are always 90 degree, or the electric field lines are always perpendicular to the equipotential surface, and two equipotential surface never intersect each other, because if they do so, such that here is a surface and here is another surface. If these two surfaces intersect each other at this position, the potential will be due to this surface and also due to this surface. So at a single point we have two potentials, which is quite impossible. So two equipotential surface can never intersect each other. And there are some more properties regarding the equipotential surface. You can refer to your notes. Okay. So what is equipotential surface? The surface where each and every point are at same potential, or the potential difference between any two points is 0. Okay. So next we will discuss so next we will discuss the next chapter, that is capacitance. So what is capacitance? So as you already know that for a region, if we increase the charge, the potential will increase. So Q is directly proportional to V. If charge will increase, the potential will increase, because the potential we already know is K Q by R. So if Q will increase, the potential will increase. So Q is directly proportional to V. So from this you can write Q equal to some constant C into V. So from this C will be how much? Q by V. So this C or constant of proportionality is known as capacitance. Okay. So what is capacitance? So capacitance is equal to the amount of charge required to rise the potential by 1 volt. Clear? If we have to rise the potential by 1 volt, the amount of charge required is known as the capacitance of the conductor. Okay. So C is equal to Q by V, and it is a perfect ratio. C is equal to Q by V. C is a constant. So the capacitance is, you have to remember that, independent of Q and V. As here C is equal to Q by V, but the capacitance never depends upon charge and potential. It is always constant. It is independent of Q and V. It's a constant. So it is independent of Q and V, and it only depends upon the shape, size and surrounding of the conductor. Okay. Shape, size and surrounding of the conductor. The capacitance depends upon what? The shape, size and surrounding of the conductor. So we already know this is capacitance, and its unit will be how much? 1 coulomb by 1 volt in SI, or this will be 1 farad. Okay, and in CGS it will be 1 stat farad. Clear? So now we have to find out the capacitance of a isolated spherical conductor. So we already know that if there is a conductor of radius r which have charge q and as all the charge resides on the surface of the conductor, we can assume that the total charge is concentrated at the center of the conductor. So what is the potential? kq by r on the surface. So what is the capacitance? C will be equal to how much? Q by V. So from this we can write C equal to Q divided by kq by r, or this can be written as r by k, or C equal to 4 pi epsilon naught r. That means the capacitance of a isolated spherical conductor is directly proportional to radius. If we increase the radius, the capacitance will increase. Clear? And it also depends upon the shape. That means if the shape will be like this, so at this region the charge density on surface charge density will be more. So if we increase the charge may have chance to discharge from this region, because here the surface charge density will be more, which will be known as the corona discharge. So the capacitance may decrease if the size or shape of the surface is not uniform. Where the local radius of curvature is less, at that position the surface charge density will be more, so that at this region the charge may have chance to discharge. That's why the capacitance of a spherical conductor depends upon its shape also, and also with the radius. Clear? So next we have to discuss what is parallel plate capacitor. So as you already know, a single conductor can also behave as a capacitor, but if we want to increase the capacity of a single conductor, so we have to take a parallel plate capacitor. What is the principle of parallel plate capacitor? The principle of parallel plate capacitor is when we brought a uncharged conductor close to a charged conductor, its potential decreases, due to which the charge storing capacity of that conductor will increase. That's the principle of what? Parallel plate capacitor. So in parallel plate capacitor there are two parallel plates of plate area A, and separation between them is D, which are connected across a cell of potential V, due to which if an electric field is generated across the gap between the plates, which can be defined as sigma by epsilon naught, because the electric field due to this plate having positive charge and this plate having negative charge will be how much? Due to this single plate, the field within this will be sigma by 2 epsilon naught, which is along this direction, and due to the negative charge plate, the field at this region will be again sigma by 2 epsilon naught, but the direction will be same as that of this one. So the net field will be how much? Sigma by epsilon naught, E net. So what is the potential difference between these two regions? We know potential difference equal electric field into distance. So the potential difference will be E into D, that will be sigma D by epsilon naught. So from this we can calculate C equal to Q by V, which will give us A epsilon naught by D. Clear? This will be the capacitance of the parallel plate capacitor. Okay, where A is the surface area, epsilon naught is the permeability of the region or the space between the plates, and D is the separation between the plate. So this will be what? The capacitance of a parallel plate capacitor. Okay. So now what is the energy stored within a capacitor? As we have to do some work by the external source to store charge within the capacitor. So the work done to give charge to this plate of the capacitor will be stored within as potential energy of the capacitor, and this energy will be how much? We already know the formula for the energy is half Q square by C, or this can, where Q is the total the charge associated with the plates of the capacitor and C is the capacitance of the capacitor, or this can also be written as half C V square, or this can be written as half Q V. V is the potential and Q is the charge of the parallel plate capacitor. So this is the formula for energy stored in the capacitor, and the derivation for this derivation you can refer to the previous lecture or to the notes that's given to you. Clear? Then we have to discuss what is the energy density. So energy density of a capacitor will be how much? Energy divided by volume of the capacitor. So from this we will get energy is how much? Half C V square divided by volume of the capacitor will be cross sectional area into D. So by solving this we will get it will be half epsilon naught E square. This will be the energy density or energy per unit volume of the capacitor, which will be half epsilon naught E square. E is the electric field intensity within the region of the plates of the parallel plate capacitor. Okay, so this is the energy density, this is the energy stored in parallel plate capacitor, and we already know what is the capacitance of a parallel plate capacitor, that is A epsilon by D. So next we will discuss the combination of capacitors, that is in series and parallel grouping. So in series grouping of capacitor, we know the charge remain constant. In series grouping of capacitor, we know if this is C1, C2, C3, C4. Here the charge across all the capacitor remain constant, but potential will be different. So the potential will be additive. So V net will be equal to how much? V1 plus V2 plus V3 plus V4. So the C equivalent can be written as 1 by C equivalent equal to 1 by C1 plus 1 by C2 plus 1 by C3 plus 1 by C4. This will be the equivalent capacitance of the capacitors connected in series, and same as that of for parallel. If there are parallel capacitors C1, C2 and C3 connected across a cell, the equivalent capacitance C equivalent will be C1 plus C2 plus C3. Here the charge is additive in nature. The potential across each capacitor remain constant, but the charge will be different. So the equivalent capacitance in parallel combination will be C1 plus C2 plus C3. In series combination will be 1 by C equivalent equal to C1 plus C2 plus C3 plus C4. Clear? And you have to remember this formula for solving numericals. Next, what will be the energy in case of series? As in case of series combination of capacitor, charge remain constant. So we know the energy for U1, that is C1 will be half Q square by C1. For U2 it will be half Q square by C2, and adding all these we will get how much? U1 plus U2 plus U3 and so on will be the U net, the total energy stored in all the capacitors. Similarly, in case of parallel, if there are different capacitors connected in parallel, C1, C2 and C3, for each capacitor the potential remain constant. So energy stored in first capacitor will be half C1 V square, for 2 it will be half C2 V square. So similarly we can write U3 will be half C3 V square, and U net will be how much? Again half C equivalent into V square, or this will be U1 plus U2, or this will be how much? U1 plus U2 plus U3 and so on, because by adding this we will take common half V square common, that will be C1 plus C2 plus C3. So total will be U1 plus U2 plus U3, and same in this case of series. So in series parallel combination, the net energy stored in all the capacitor will be simply the algebraic sum of the energy stored in each capacitor. Clear? So next, what will happen when we introduce a dielectric in a capacitor? If a dielectric is introduced in a capacitor, what is a dielectric? Basically, dielectric is a insulator which have no free electrons. So when a dielectric is introduced in a capacitor, basically dielectrics are of two types. One is polar dielectric and another one is non-polar dielectric. Polar dielectrics are the dielectrics in which the center of the all positive charges and center of the all negative charges are separated by a certain distance. So they have some permanent dipole moment. Okay, but due to thermal motion, the net dipole moment of the dielectric is 0. But in non-polar dielectric, the center of mass of the all positive and negative charges coincide. So they have no permanent dielectric moment, no permanent dipole moment. But when we apply some external field, the non-polar dielectric have some dipole moment, and when the external field is absent, the net dipole moment is also 0. They have no permanent dipole moment. So when a dielectric is placed in an external electric field, it gets polarized. That means the opposite faces of the dielectric acquires oppositely charged. If here is a plate which have positive charge and here is a plate which have negative charge. So there will be external electric field along this direction. This will be E naught and this is a dielectric. So it will have negative charges on this surface and positive charges on this surface due to induction method. So there will be a induced electric field in the dielectric along this direction EI. So what will be the net electric field in this dielectric? Within it will be E naught minus EI, because E naught is along this direction, EI is along this direction. So this is the E net inside the dielectric. So what is dielectric constant K of this dielectric? K equal to total external field divided by total internal field. So this can be written as E external will be how much? Sigma by epsilon naught divided by sigma by epsilon naught minus sigma I, the surface charge density due to induction, divided by epsilon naught. So this implies you will get K equal to how much? Sigma by sigma minus sigma I, and by solving this we will get the induced surface charge will be sigma into 1 minus 1 by K. You have to remember this relation. What is K? K is the dielectric constant of the dielectric. Clear? So what will happen? And this process, when a dielectric is placed in an external electric field so that it will acquire opposite charges on the opposite faces, this process is known as polarization of the dielectric, due to which it has some net induced electric field within it. Clear? So what will happen when a dielectric is introduced in a parallel plate capacitor? So when a dielectric is introduced in a parallel plate capacitor, if here is a parallel plate capacitor, area is A, separation is D, okay, connected with the potential V, and a dielectric slab of dielectric constant K and thickness T is introduced within the parallel plate capacitor. So its capacitance will be A epsilon naught divided by D minus T plus T by K. What is T? T is the thickness of the dielectric slab, K is the dielectric constant, and D is the separation between the plates. A is the area of the plate and epsilon naught is the permittivity of the free space. So this will be the capacitance of a parallel plate capacitor having dielectric slab partially filled within it, and the position of the dielectric slab is independent. You can place any place within the region of the plates. If the total space within the parallel plate capacitor is completely filled with dielectric, so for this T will equal to D. So if T will equal to D, this term will become 0. So we will get A epsilon naught K, T will be D. So this will be the total capacitance of the parallel plate capacitor when the complete space between the parallel plates are filled with a dielectric slab of constant K. And for the derivation you can refer to your note or the previous lecture. Okay, this will what happen when a dielectric will introduced in a parallel plate capacitor. Okay. So next there is a important concept that if two capacitors are connected in parallel, then what will be the common potential? If initially this is having capacitance C1 and potential V1, this is have capacitance C2 and potential V2 initially, and there is a key which is not closed, and this is the case when the key is not closed. When we close the key, these two capacitor will connected in parallel, then what will be the common potential? After the closing of the key, the common potential will be C1 V1 plus C2 V2 divided by C1 plus C2. Clear? You have to remember this, and this is the formula when the positive plate of both the capacitors or both the capacitors are connected in such a way that their corresponding plates are same. That means plus to plus and minus to minus. When the plates are opposite, that means it is connected like this. This is positive negative, this is negative positive. When the key is now closed and initially C1 V1 and C2 V2 are the potential, then the common potential V will be C1 V1 minus C2 V2 divided by C1 plus C2. So in this case initially it have some energy which can be written half C1 V1 square and it have half C2 V2 square. So what will be the energy after closing the key? The energy U will be half C1 C2 divided by C1 plus C2 into V1 minus V2 square, and here it will be U, the change in energy delta U, which will released as in form of heat will be half C1 C2 divided by C1 plus C2 into V1 plus V2 square. This is the change in energy or the amount of heat produced when the capacitors are connected in parallel such that their opposite plates are connected together, and this is the relation when the same polarity plates are connected together. And for the derivation you can refer to your previous lecture. Clear? So you have to remember this formula for the common potential when two capacitors are connected in parallel, and the heat released or energy difference initial and final will be this much. Clear? So next there is an important question which I will just telling you the concept that if there are n number of small droplets, if there are n small drops of radius r having charge q which are combined to form a large drop of radius r, then what will be the potential of the large drop? If there are small drops, n number of drops of radius smaller and each having charge q, so which is formed, the small drop is formed to form a large drop of radius r, then what is the potential of the large drop? As we know, for the each small drop, the potential for each small will be how much? K q by r. As there are n number of drops, the net potential for small will be how much? N K q by r. And as the all drops are combined to form a larger drop of radius r, so the volume remain constant. So 4 by 3 pi capital R cube will be equal to n into 4 by 3 pi small r cube. So from this we will get what? R equal to n to the power 1 by 3 into r. And the charge is also conserved. So the total charge on the larger drop q will be how much? N into q. So this implies you get the potential of the large drop equal to K into N into Q divided by, in place of R you can add N to the 1 by 3 into R. So this can be written as K Q by R into N to the power 2 by 3, because 1 by 3 taking off it will be 2 by 3. What is K Q by R? K Q by R is the potential due to a single small drop. So the potential of the large drop will be equal to n to the power 2 by 3 into potential due to a small drop. What is n? The total number of drops which are combined to form the large drop. So this is an important concept, may ask in form of numerical. So you have to remember this relation. Okay. So this is about your electrical potential and potential energy and the capacitance. So refer to this video for your revision purpose. If you want to go through this concept properly and thoroughly, refer to the previous lectures that sent to you. Okay, thank you. All the best.